right, so this is about doubly efficient zkSNARKs without trusted setup. So zero knowledge, succinct, non-interactive argument of knowledge, or a zkSNARK. These have been the subject of some intense research interest, and more recently, even some interest in the broader tech world. So I'm going to tell you about some of the work that my co-authors and I did, but I'm also going to try and give you a more general picture of the area and other systems in it. So first, let's try to cut a little bit through the jargon. What is a zkSNARK? Well, so it's an argument. That is, it's a proof, but one whose validity depends on some cryptographic assumption. And it's an argument of knowledge, which means you can use it to prove, roughly speaking, that you know a secret. And it's zero knowledge, meaning that when you use it to prove that you know a secret, you don't reveal anything about that secret. Now, the proof is succinct, meaning that it's short, and it's non-interactive. So it can just be written down, and then later somebody can come and read it. It doesn't require any kind of conversation. And finally, we're concerned about publicly verifiable proofs, meaning anyone who reads the proof will be convinced of its validity. So when we compare these different kinds of SNARKs, there are at least 5 questions that we can ask. One is, how big is the proof? We said it was small, succinct, but some kinds of zkSNARKs are smaller than others, and generally speaking, argument systems may or may not be succinct. Proof size is important, for example, if you're going to be sending the proofs over a network, or if you're going to be storing many proofs for a long time. Another question is, how hard is it to generate a proof? That is, how much time does it take to write down the contents of the proof? And relatedly, how much time does it take to check the proof? Okay? And throughout the talk, you're going to see these script P and script V. Those refer to the prover and the verifier, the entity that generates the proof and the entity that checks the proof. Okay, so remember, the validity of these proofs, since they're arguments really, depend on some cryptographic assumption. So another question we can ask is, what is that cryptographic assumption? And we might care about this because, as you would guess, the cryptographic community has reason to believe that some assumptions are better than others, maybe because they've been battle tested for longer. And finally, some zkSNARKs, including the ones that are currently most widely deployed, like in Zcash, require a trusted setup, meaning that somebody has to run an expensive one-time computation, and you can only believe a proof is valid if you trust the entity or entities that ran that setup computation. So you can see already this is a big design space, and every kind of zkSNARK and every kind of zero-knowledge proof system more generally gives some different mix of these properties. So the zkSNARK my co-authors and I designed, we call it Hyrax, and it represents sort of a new point in the space. Hyrax proves the satisfiability of arithmetic circuits. We'll see what that means in more detail soon, but for now, imagine that we have some computation C that's a circuit, and that is to say, sort of has gates in it. We'll get into more detail on that soon. And the prover convinces the verifier that it knows some value W, which we'll call the witness, that makes the computation or the circuit output true. Now, for efficiency, Hyrax requires that the computation has some kind of repetitive structure. For example, it could be many parallel copies of the same computation, or it could be repeated instances sort of in series of a computation. Again, we'll see a little bit more on that later. Now, in terms of the 5 costs we just saw, Hyrax has proofs that are concretely and asymptotically small, and the prover is concretely fast and asymptotically optimal. The verifier is also fast, and it's slightly work-saving, which is to say, for big enough circuits, the verifier has to do less work to check the circuit, to check the proof, than it would have to sort of check the witness itself. And finally, Hyrax relies on the discrete log assumption, and it needs no trusted setup. So these are all sort of asymptotic statements or sort of general statements, but you might ask sort of more concrete, more practical questions, like how does it compare to other systems? And so that's what we did. We ran several other SNARK systems, and we sort of did a concrete comparison. And I'll tell you more about this later, but the upshot is that Hyrax gives small proofs in the sense that if you wanted them to be smaller, it seems right now like you would have to pay more in terms of prover or verifier computation, or both. And Hyrax is fast, meaning if you want the prover or verifier to get faster, it seems like you have to accept bigger proofs. So that's not to say that Hyrax is anything like the best proof system. It's not, because there isn't a best one. This isn't a competition, and there isn't a winner, right? This is a design space, and there are different applications that might use designs in this space. So when you go shopping for a zero-knowledge proof system, decide what's important to you, and choose the correct system, the system that matches up with that the best. So that's what we're going to do. We're going to start by taking a look at some of the design space of general-purpose zero-knowledge proof systems. And later, we'll look more at Hyrax's design and then some of the evaluation results I mentioned. So when we talk about general-purpose proof systems, usually we mean proof systems for NP languages. So what that means is there's some relation R, and we can think of that as a computation that takes some values and then returns true or false. Now the values are an input, X, from the verifier, and a witness, W, from the prover. And we can think of the witness as a secret that the prover knows, and R, the relation, as a computation that checks whether the witness is somehow correct for the verifier's input. And at a very high level, these systems all operate by turning the witness checking computation into sort of two different computations. One that's the verifier's job, and one that's the prover's job. So we can think of this as sort of happening in two stages, which we'll call the front end and the back end. Now, in the front end, we convert the witness checking computation into an arithmetic circuit, which is to say a generalized Boolean circuit, where we can think of AND gates as becoming multiplication and OR gates as becoming addition. And the front end constructs this arithmetic circuit such that its satisfiability is tantamount to the correct execution of the witness checking computation. Okay? Then the back end applies proving machinery, which is some combination of complexity theoretic and cryptographic objects, to produce a prover and a verifier computation such that a valid proof establishes that the circuit is satisfied, which, by the implication in the front end, establishes that the witness checking computation was run correctly. So up to this point, I've been talking about different kinds of zero-knowledge proof systems, and really what I've been referring to is that proof machinery in the back end. So we're going to focus in a little bit more on that. Let's take a look at how some of the existing systems work. So maybe the most well-known zero-knowledge proof systems are Pinocchio and libsnark. These are used, for example, as I said earlier, in Zcash. Now these are built on an object called a linear PCP, and very roughly speaking, their properties are such that they give short proofs and very fast verification, but proving is slow, and they rely on cryptographic assumptions that are non-standard, that we don't trust them maybe quite as much. And finally, they require a trusted setup. Somebody has to do that initial computation. Now, earlier today, you saw a talk by Benedict on bullet proofs, and this relies essentially on a different kind of linear PCP and some different crypto. And the result is that bullet proofs gives short proofs, and unlike libsnark and Pinocchio, it uses standard cryptographic assumptions, and it requires no setup. On the other hand, there's a little price, and that is that the proving and especially the verifying gets a little bit slower. An entirely different class of proof machinery comes from multi-party computation in the head, which is due to Ishai et al. And zkBoo and zkB++ are sort of the first practical implementations of this paradigm, and they have fast proving, they build on a standard cryptographic assumption, and they have no trusted setup. But they give long proofs, and verifying is slow-ish. What does that mean? Well, the asymptotics aren't great, and they kick in sort of even for moderately sized problems. So for very small computations, these are blindingly fast. But for bigger computations, maybe think again. So more recently, Ligero improves on the approach from zkBoo and zkB++, and it uses some different sort of complexity theoretic objects to give shorter proofs and faster verification. I still say ish here because compared to libsnark and bullet proofs, the proofs are still longer. And compared to libsnark, the verifying is still much slower. Okay, and finally, there's this newest class of machinery, in some sense building on the oldest class of theory, it's short PCPs. And libstark is right now the only practical implementation of this approach, and it gives short proofs and fast verification, and it needs no trusted setup. But proving is slow, and it relies on an unproven conjecture that has some relation to the hardness of Reed-Solomon decoding. So this table is not gospel, it's just a rough approximation of the state of play. But the important thing to get from it is that there are all these different systems that you might pick depending on which of the columns is most important to you. And none of them really is clearly best among these. Right? Okay, so with that landscape in mind, let's take a quick look at Hyrax's machinery. So HIRAX is built on a completely different thing called an interactive proof, which is essentially a probabilistic cross-examination. And we make these interactive proofs of zero knowledge using techniques of Ben Orr et al. And Kramer and Damgaard. But as we'll see, naively applying those techniques results in poor performance. So in HIRAX, we also include several refinements, which result in order of magnitudes improvement in both verifier time and proof size, and small constant factors in improvement for the prover as well. So the high-level idea in HIRAX is that in an interactive proof, the verifier is sending questions and the prover is sending answers to those questions. And what we're going to do is replace all the answers that the prover sends with cryptographic commitments to the answers. And then the prover is going to help the verifier to check that the contents of the commitment are actually a message that would have been valid in the sort of underlying interactive proof without revealing anything else. So to review, let's take a look at a cryptographic commitment. So in a cryptographic commitment scheme, we have a sender that computes a commitment to a message, and then it sends the commitment to a receiver. Now, later, the sender can open the commitment and then reveal the message inside and convince the receiver that the message that's revealed is consistent with the commitment that was sent earlier. So generally speaking, commitment schemes have two properties that we care about. Hiding means that the commitment reveals nothing about the message inside, and binding means that the sender can't lie when it tries to open the commitment. It can't decide, well, I really wanted to send this other message, so I'm going to do that instead, because it'll get caught cheating. So HIRAX uses a special class of commitments that have sort of a third property, a linear homomorphism, which means there's some operator that we can use essentially to add two commitments together. So when we do that, we get a new commitment that has inside of it a message that's the sum of the two. And from that, you can get sort of scaling by some constant factor because you can just add the same message to itself many times. Okay, so the other thing that HIRAX builds on is an interactive proof, and specifically one due to Goldwasser, Kalai, and Rothblum. This is an interactive proof for layered arithmetic circuit evaluation, which means that the inputs to the circuit feed one set of gates, and the outputs from those gates feed a second set, the outputs from those feed a third, et cetera. So to start the proof, the verifier gives some inputs to the prover, and then the prover is going to evaluate the arithmetic circuit and produce some output, y, that it's going to send to the verifier. Now, the verifier and the prover start to interact. So first, the verifier is going to construct a polynomial that relates the purported output, that's y, to the last layer of gates in the circuit. Then it's going to engage the prover in what's called a sum check protocol. This is sort of a foundational interactive proof. And the result of that sum check protocol is a claim about the second last layer of the circuit. Now, in some sense, that's not good enough because the verifier can't check that very easily. So what do the verifier and prover do? They continue to interact. So now we run another sum check and we get a claim about the prior layer. And we keep doing that, and eventually we get a claim whose truth is related to the inputs to the computation. Now, in a non-zero knowledge version of GKR, this would be it. We would be done because the verifier has those inputs and it can just check that claim directly. But in zero knowledge, we need to make two modifications. So the first one, as I said earlier, is that the prover is going to replace all of its messages in the sum check invocations with commitments to those messages. And the second, and this one's a little more complicated, is that we need to give the verifier some way to check that final statement in the proof. And remember, the verifier never gets to see the witness. And since this is a witness-checking computation, somehow the inputs have to encode the witness. So the verifier certainly can't check that directly. So what's it going to do? Well, we're going to use what we call a polynomial commitment scheme. So the final check that the verifier needs to do is just evaluating a polynomial that we'll call tilde m. And this polynomial encodes both the input and the witness. Now, to run the check, the prover will send a commitment to the verifier at the start of the protocol, so before any interaction happens. Okay, then the prover and the verifier are going to run the interactive proof that we just saw on the previous slide. And at the end, the prover is just going to make a claim. It's going to say, here, the evaluation that you really want is this one, is this value here. And finally, the prover and verifier are going to engage in an additional protocol that convinces the verifier that the output that the prover just claimed is consistent with the commitments that the prover sent at the beginning of the protocol. So HIRAX uses a new polynomial commitment scheme for multilinear polynomials, which is what m tilde is. And I'm going to show you a little bit about how that works now. So these multilinear polynomials have a specific form. Namely, we can think of them as a vector matrix vector product. So the vectors L and R depend only on the point at which we evaluate the polynomial, and the matrix T encodes the monomials of tilde m. In our case, the matrix is encoding W, the witness. So a naive approach is that we would just build a polynomial commitment scheme by having the prover commit to each element of the matrix T individually. And I think if you think about it, you'll see that that's enough already, because since these commitments, as I said earlier, have this linear homomorphism, we can already compute a vector matrix vector product just by using that homomorphism. Okay? But that's inefficient. Why? Well, the commitment size and the work to do the polynomial, to compute the commitment to the polynomial is linear in the size of the witness, right? So as the witness gets bigger, it scales linearly, and we'd rather scale sublinearly. So to sidestep that problem, we're going to follow an idea due to Jens Grunt, who uses multi-commitment schemes to commit to each row of the matrix. So what's a multi-commitment? Well, it's a commitment where the message inside is a vector. And if we use the Peterson commitment, then what we get is a multi-commitment that has a vector-wise homomorphism. So if we have two commitments to vectors and we use the addition operator on them, what we get is a commitment to a new vector that's the sum vector-wise of the previous two. Okay, so then how are we going to use this? Well, the verifier is going to compute the vector matrix product L times T by itself using that vector-wise homomorphism. And I think we can see how that happens. The entries of L are each scaling one row of the matrix T, and then we sum those scaled versions together. And then second, the prover is going to send a commitment to a claimed evaluation of tilde m. And then finally, the prover is going to use what's called a dot product argument or an inner product argument to convince the verifier that the claimed evaluation is consistent with the vector R and the vector matrix product L times T that the verifier previously computed. Now, if this sounds familiar, it's because you've already seen this earlier today in bullet proofs. In fact, we adapt the dot product argument from bullet proofs, and the result is that this has some kind of very low cost in terms of the communication. Specifically, it's logarithmic in the length, in sort of the number of columns in the matrix. So that means if the matrix is square, then the prover is going to send one commitment per row, plus a logarithmic number of extra messages that we don't need to worry too much about. They're small. And the verifier's computation is going to be proportional to the sum of the number of rows and the number of columns. And in total, both of these are just sort of square root-ish. Okay? But alternatively, what we can do is we can adjust the size of the matrix. We can make it sort of fewer rows and more columns. And what that means is that the prover ends up sending less information to the verifier, and then the verifier ends up having to do a little more work to sort of compute over the columns of the matrix. What this means at the end is that you can tailor hierarchs to your application's needs. If you need less communication, you can pay for it with a little bit more verification time. Okay, so I've described everything in terms of an interactive proof. To get it non-interactive, we use the Fiat-Shamir heuristic. And we give several other refinements that I'll leave to the paper, but I'll just mention them quickly here. First, we also use these multi-commitments to save proof size and verifier work in the sum check invocations. And second, we develop what we call a redistribution layer, which, remember I said we need some sort of repeated structure to the computation. The point of the redistribution layer is to sort of give us a wider range of computations that we can turn into something that has the appropriate repeated structure. And finally, we tweak the giraffe interactive proof, which is prior work, to make giraffe++, which reduces the proof size somewhat further. Okay, so let's take a look at the evaluation results. So our points of comparison are 5 existing systems. That's BCCGP square root, bulletproofs, zkB++, Ligero, libstark, and then also 2 versions of hierarchs. One where the matrix T has sort of twice as many columns as rows, and we use the polynomial commitment scheme trick that I described earlier. And the other where we leave off all the refinements. We just do the naive, straightforward thing. So the idea there is let's see how much those refinements help. And don't worry too much about memorizing the legend. I'll repeat it on the next slides, I promise. So we compare these systems at 90-bit security, which arguably is too low, but maybe is sort of the starting point for what you might use for a non-interactive proof. And the benchmark I'm going to show you is what's called a SHA-256 Merkle tree. So in this benchmark, the prover is going to convince the verifier that it knows all the leaves of a hash tree that correspond to a root that the verifier holds. Okay, so first up is proof size versus log of the number of leaves in the hash tree. So both x and y axes are effectively logarithmic, and the green dots are hierarchs. So remember, hierarchs lets you tailor the proof size and the verifier time, and as I said earlier, we tailored it to sort of a short, fat matrix. So what I'm showing you here, I call hierarchs 1/3. And the result of that sort of tailoring is that the hierarchs has kind of the second best proof size among these systems. But you can see that bulletproofs has much, much better proof size, much smaller. And on the other side, zkBoo, the red squares, has these very large proofs. And the naive version of hierarchs, where we don't apply any of the optimizations, is even worse, right? It's huge, huge proofs. Okay, but what that means is, in some sense, the refinements are working already, right? We can see that they improve the proof size. The next up is prover time. Again, this is log scale. And remember zkB++, remember you'll see it had the biggest proofs, but now it also has the fastest prover, right? So if you need a screaming fast prover, you choose zkB. Ligero's prover also has a good showing, and then hierarchs is kind of next up. And what you see is that whereas bulletproofs had sort of a very small proof, you pay for that by having to sort of work harder to generate that proof. Right? And this is sort of a theme that we'll see a couple more times. And finally, you can see there's kind of a small constant factor, maybe 3x, between the blue stars, that's the unrefined version of hierarchs, and the green diamond, or the green hexes, the refined version. Finally, let's look at the verifier time. So here, libstark has far and away the best performance, and Ligero, again, very good performance and speed. For big enough problems, hierarchs is faster than zkB++. So remember what I said, the verifier in zkB is kind of slow-ish or fast-ish, depending on how you think about it, because once the problem gets big enough, then the verifier time starts to run away. And finally, this is another case where the improvements from hierarchs, the difference between the blue stars and the green hexes, is really big. So those refinements really help in terms of the verifier time. Okay, so let's conclude. I've showed you hierarchs, which is sort of a new general purpose zkSNARK. And as we saw, hierarchs gives you kind of small proofs in the sense that if you want them to be smaller, you've got to use a system with more prover and verifier cost. And it's fast in the sense that if you want faster, you have to pay for that in bigger proofs. But again, the most important takeaway here is that there's no real winner because there's no actual competition. Different proof systems give different combinations of properties, and what we should be doing is thinking about our application carefully and then choosing the one that applies. So hierarchs, from that point of view, is just a point in the design space, and of course there are other points in the design space that are even better that we haven't reached yet. So there's plenty more work to do. Our paper and our code are available online, and I hope you'll check them out. And with that, I'll take any questions.
Any questions? So why do you think there isn't going to be a proof system that just dominates everybody else in all coordinates? Maybe that might happen.
I mean, I think we should hope for it in the sense that it would make our lives easy. We'd just run that proof system and be done, and then everyone could concentrate on improving it and making a nice implementation. But it's slightly, I think for now, magical to hope for it in the sense that everyone is using certain tricks to get their good points, and in the end, that's what's producing their bad points.
Any other questions? All right, thanks, guys.